Today we're going to look at PID controllers. Again, we started in the last lecture, but we only covered PI controller. There is proportional integral. We left out the derivative part, so let's bring the derivative part in today and see what that does. It's basically an extension of what we saw there. So to recall the last lecture, we had two elements in our controller now. The first was the proportional gain. Proportional gain will take action based on the current error. The higher the current error, the more action we give to the plant. The limitation with that was that we couldn't eliminate steady state error. We saw that the steady state error can be decreased with a proportional gain, but it can never be eliminated. And that was the idea then behind the integral gain. Because the integral gain looks at past error, it takes the integral of error over time. It will guarantee that the steady state error will be zero. Because so long as there is an error, the integration keeps building up. And it will only stop building up when the error is zero. So we can say that the integral controller will always eliminate the steady state error. But there was one problem with that. The integral gain adds more control action into the game. There is more power given to the plant. And we will start to see some overshoot, which is not always desirable. How we control the overshoot? Well, that's the job of the derivative controller, the D part, which is the one we are going to focus on today. So here is the schematic for the entire controller now. We have the same as the last week with now 3 components. The first one is the proportional controller. We gave that a proportional gain Kp. So we see here we take the desired output, we measure the current output, create an error, multiply the error by a constant, and that a constant is given to the plant. That a constant is the proportional gain Kp. In the last lecture, we also use an integral controller. So we take the integral of the error, 1 over s, multiply that by Ki, the proportional, the integral gain, and also add that to the control action. Now we are going to look at, we're going to add the derivative gain. Let's call that Kd. And you're simply going to multiply that by s, because that's the derivative operator. And now give that to the plant as well. So the output given to the plant, or the input given to the plant, the output of the controller, is now a combination of the proportional, derivative, and integral of the error. And these Kp, Ki, and Kd are simply weights that we assign to each of them. So the magnitude of the current error is the proportional gain. The integral of the error over time is the integral, of course. And now the derivative is looking at how fast or how the error is changing. We are taking the derivative of it. We're looking at the time rate change of the error. That's the derivative part. That's the newly added component. Because you look at the derivative, we can kind of predict how the error is going. Is the error increasing or decreasing? And if the error is decreasing or increasing, we can take action based on that as well. Based on how it's changing, we can anticipate future behavior and perhaps use that information to reduce overshoot. So again, Kd, Ki, that's a terrible I, Ki, and Kd. So S, 1 over S. Here we have the error, E of S, and the output is U of S. Is the control action. We had the first 2 elements before, it's just the proportional plus the integral. Now we add the derivative component. The derivative component is the derivative of the error. When you do that in the Laplace domain, it's simply the error times S times Kd. And if we factor out all the error, this is now the transfer function of the controller itself. Kp plus Ki times 1 over S plus Kd times S. So if we expand this, we have Kps plus Ki plus Kds squared, all divided by S. So we can see that this controller adds 1 pole at the origin and adds 2 zeros to the closed loop system. Adds 1 pole and 2 zeros. And then we can play around with Kp, Ki, and Kd to place the poles where we want them to be.
So let's go back. Sorry, in the last slide, should the first triangle be KP?
The last,
The first triangle.
the first triangle, K derivative, yeah, that's KP, yeah. The first gain, right? K proportional, yeah. Indeed. Right, thank you. Let's go back to the muscle example we had in the last lecture. We were trying to stretch that muscle to a given position using a motor, and that motor is providing a force that moves the mass. The objective is to move the mass by a amount of x0 and make it stop at x0 without any steady state error. Same example we did before. So we are applying a voltage to the motor, it turns into force, creates a displacement. The muscle here is represented as a mass spring damper system, can be represented like that. If you put two elements in parallel like this, one for the viscous friction and another one for its inherent elasticity. So the first attempt we did was to use a proportional controller. So here is the transfer function we used in the last lecture. We use a proportional controller to control the position. Objective was to bring it to position x0, which is now given as a step to this system. And what we saw here was a little limiting, because we saw that we could approach x0 but never get too close, never get to x0. And the reason is that now the control action, the voltage we give to the motor, becomes proportional to the error. So if there is no error, there is no voltage, and there is no action given to the mass, the muscle will simply move back because of the spring. We can increase the gain as much as is possible according to the driver we use, but there is always a limit, and based on the nature of this controller, the steady state error can never be zero. There is no way around. What we give to the motor is basically the error that we see here is simply the red curve minus the blue curve multiplied by a constant. That's the voltage we see there. Right? In the steady state, there is a voltage applied to the motor. There is a force holding the mass, but not quite at the position we want, because otherwise, if we were at the position we want, error is zero, voltage is zero. The other attempt was to use an integral controller. So in that case, we had an integral gain, and of course, we have the integrator that I forgot to put in here. Same transfer function, same system, but now the closed loop transfer function is different. And if we only use an integral gain, now we are looking at the past errors. So we are basically taking the integral of all these areas, adding them together. Right? It's the difference between the desired output, which is in red, and the blue, which is the actual output. And you're now giving that to the motor. Here we have the comparison with what a proportional controller would do. And here is what an integral controller would do. You see now that the proportional controller at the end of the cycle goes to zero because the error is zero. But now the integral controller reaches a steady state at a point where the steady state value it applies to the plant is never zero. Right? Because you're now taking the integral of zero. We build up some control action. We added all these areas together, and we ended up with a non-zero value. When the curve reaches zero, we just keep adding zero to it, right? So the steady state value is never zero, is everything we calculated in the past plus this 0, 0, 0. So the integral controller keeps applying force even when the mass stops moving, and that's what brings it now to the desired position. Even if the mass is stopped, let's say just a few millimeters before x0 and the integral gain was very small, so long as the error is not zero, the integrator continues to build up and will eventually build enough energy to increase the voltage sufficiently to create now a force that will slowly make the mass move towards its destination, at which point the error becomes zero, but the integration, because it's the past error, is not zero, and that's what guarantees that the mass stays in place. So in a steady state, the integral controller is the one providing force to hold the mass in place. The proportional controller did its job in the beginning when the error was non-zero. But we can notice something interesting here. If you compare these two step responses, the first one had a little overshoot. The second one has much more overshoot. Well, that's expected because we added more control action to the system to eliminate the steady state error. In the first one, we only had the proportional error, proportional controller. Now we have an integral controller that is adding this much more control action to the plant. Remember that they are added together and the result is what we give to the plant. So especially in the beginning there, you see that there's a lot more energy provided to the mass. So it will accelerate faster and it will eventually overshoot its final destination before it bounces back to settle at that position. And that's the main limitation of the integral controller, is this extra energy provided to the plant will eventually make it overshoot. We will accelerate the mass has some inertia, and once we reach the point where we reach x0, the desired point, the proportional controller can turn off, but now the mass has some inertia, we'll keep going, right? And we'll keep going and overshoot. Now, how do we fix that? Well, that's the idea of the derivative controller. We can simply add another branch here to our controller and make it proportional to the rate of change of the error. We are taking the derivative of something. We are looking at how basically it is changing over time. So if you multiply this by an error derivative, add that to the proportional controller. Here we have a proportional derivative controller. So let's see what happens here. We are still want to put the mass to go to position x0, and let's assume that it is doing something like this to start. It is moving towards its destination. What is the error? Well, the error starts at x0. So this is the error. And it slowly decreases. What is the derivative of the error? So the error dt. Well, the error is decreasing, right? So if the error is decreasing, its derivative is basically the slope of this curve. We are taking the slope of the curve at any point here, calculating the angle of that curve, and that's the slope, and which corresponds to the derivative. And you can see that it's negative. It's negative because it is decreasing. So the error will probably jump like that and then eventually go back to 0, the derivative of the error. We are now adding these two together, and this becomes the voltage we apply to the motor. So what are we doing here actually? Well, let's think about it. We are looking at how the error is changing. When the error is decreasing, the derivative gain is negative. The derivative controller is negative because the derivative of the error is negative. When the error increases, then the derivative of the error becomes positive. And we are adding all this together and sending it to the plant. So now, in this particular case, the error is decreasing. And what we are saying is, because the error is decreasing, because we are taking the right action to decrease the error, we can in fact decrease the control action given to the plant. We are now adding these two together. So we are actually providing less control action than the proportional controller by itself, because we are adding to the proportional controller, which would be just this error times a constant. We are adding a negative value to the voltage we apply to the motor. And why is negative? Because that's the derivative of the error, which is decreasing, gives a negative voltage, which in other words means we are going towards the destination we want. The error is decreasing over time. The control action we are taking is effective in decreasing the gain. So if that is the case, let's decrease the control action so that there is no overshoot. It could be the opposite. We could also have a curve that would maybe overshoot a little bit like this. All right, so what would be the error? The error would be positive and negative in some instances. It would be something like that. And for some parts of the error would be negative, then it becomes positive, then it becomes negative. The derivative now would take positive and negative values, meaning that as when the error is decreasing, we decrease the control action because we know we are moving towards the goal. When the error increases, we further increase the control action because we are now going away from the goal we want. And once the error starts to decrease, we decrease the control action once again. And that's the idea behind the derivative controller. We could say, it's a bit of a stretch here, but we could say the derivative controller is predicting the future behavior of the system and then taking action before that takes place. It's looking at the rate of change. It's looking at how the system will be in a few seconds ahead, if you're going towards the destination or not. And then based on that, we adjust the gain. We adjust the control action based on that, right? So in this particular case, if you only had the proportional controller for this curve here, we would apply more energy to the system than if we had a proportional derivative controller, because as the error decreases, we have a negative gain. Negative gain takes some of that control action out and compensates for the fact that we're moving towards the destination. And luckily, and hopefully that decreases the overshoot. Okay. Now, is the idea, I think the idea behind the proportional, the integral is fairly easy to grasp. Is the concept of the derivative gain clear? Do you understand why the derivative gain will eliminate overshoot?
Sorry, can I ask a question?
Mm-hmm.
I understand why it eliminates the overshoot, but I don't get how it makes our error to actually become zero. Because we said if we have only the proportional controller, it never becomes zero.
Yeah.
But here, for example, in this very example, we have only proportional and derivative controllers, and we can see that the error actually became zero.
Well, that's the imprecision in my drawing here, because it should indeed not go to zero. It should stay a little above zero. Just that it's hard to draw. But that's actually a very good point. Very good point. So the error is indeed not zero. Let me ask you this then. What would be the influence of the derivative gain in a steady state? What would it do in a steady state?
Approach but never reach zero?
It will never reach zero. Yeah, yes, it may never reach zero. But what is my question is more, when we reach a steady state for the proportional gain, we saw that if the error is zero, it doesn't do anything. We saw that the integral gain is the one in a steady state holding the mass at a given position. In a steady state, then what does the derivative gain do?
Nothing.
Nothing. Exactly. Very good. It does nothing because we are taking the derivative of the error, and in a steady state, the error is constant. It's either zero or non-zero, doesn't matter, but it's constant, and the derivative of a constant is zero. So what is the influence of the derivative gain in the steady state error?
It has no influence?
Has no influence. Very good. It has no influence because in a steady state, once again, the error is a constant, either zero or not. It's a constant, and the derivative of a constant is zero. The derivative gain does nothing in a steady state and does not help the system reduce a steady state at all. It only operates during transients. Right? It only operates during the transients, during parts where the error, cycles where the error is changing over time. Very good. Are there any other questions there? No, so let's see. So I told you that it doesn't do anything in a steady state. So let's calculate the steady state error. And if I'm right, the steady state error should not be a function of KD. So the transfer function for this closed loop system, if you do x over xd, x of s over x of t is actually already gave it there. That's simply the closed loop transfer function. You know how to calculate that now. That would be it. The steady state error is the limit when s tends to 0 of s times the error, which is the same as the limit when s tends to 0 of s times, what is the error? The error is xd minus alpha kds plus kp divided by s squared plus s times b plus kd alpha plus k plus kp alpha. All this times x of d. So this entire thing here is simply the output x of s that I took from this expression by simply multiplying both sides by xd. We can factor out xd of s, which is the desired input. What does it give? So it gives s times xd. Let's assume a step input, so xd equals to 1 over s. And this becomes 1 minus this whole thing. Oops. This arrow is there. There we go. All right, so this, remember this one here is xd of s that I'm assuming to be a step. What is the final result here? Is 1 minus all s's go to 0. That goes to 0. This goes to 0. This entire thing goes to 0. We have 1 minus alpha kp divided by k plus kp alpha, which is the same as k over k plus kp alpha. Sorry. Yeah. I just divide everything by, find the common denominator, and that simplifies. So now notice the steady state error here. K is the stiffness of the spring, so we can't change that. The only thing that we have control over is Kp, which is the proportional gain, not the derivative gain. So the observations we made previously is still hold here. The proportional gain helps reduce the steady state error. Can never eliminate the steady state error because you can never make this expression 0 by changing Kp. And we can further conclude that a Kd, the derivative gain, is not part of it. The steady state error is independent of the derivative gain. And makes perfect sense because in steady state, the error is 0, is a constant, its derivative is 0. Okay, so here we have the final version of the controller, all the elements combined, the final expression for the control action that is now a function of the current error, proportional, past error, integral, future error, derivative, all combined in one. Now notice this block here is a bit odd. This is the S operator, but if you use a Simulink and you put a transfer function with the S, it's not going to work because there we have a what we call an improperly defined transfer function where the degree of the numerator is greater than the degree of the denominator. And Simulink doesn't accept that, so here's a little trick to make that go through. If we make S alpha a very large number, this works like a high pass filter, a low pass filter with a very high cutoff frequency, and works like a derivative operator. It's just a trick to be able to implement this in Simulink if you have to. Okay, but it's essentially the S operator. Okay, so now that we already talked about the effect of the derivative gain when it comes to the steady state error, let's look at the other metrics here. One of them was, of course, the overshoot, and that's the main thing we are looking at. So if you take the transfer function for this particular example here, we have a generic plant there. We have a Pid controller. Here's the P, here's the D gain. If you find the transfer function between y and x, which you should be able to do easily now, here is the transfer function, right? Y over x. And we can now define here the damping ratio, the natural frequency, everything, and calculate percent overshoot and the settling time. We know that the final value does not depend on kd, thus it has no effect on the steady state error. That's what we just did. From this characteristic equation, we can take the damping ratio and the natural frequency. We know that this element here is omega n squared. We know that this element here is 2 zeta omega n from the standard form of a second order equation. And you can now equate them to find zeta and omega n. So here's the expression for zeta. You see that zeta is a function of kd, the proportional gain, and the derivative gain as well. And we can also see that omega n is a function of kp. More importantly, if you look at this relation here, we see that the damping ratio is directly related to kd. The greater kd, the greater the damping ratio, which means the lower the overshoot. The greater kd, in other words, the farther we are from the imaginary axis. Remember that the damping ratio is directly related to the angle between the imaginary axis and the line that connects the pole to the origin. So the greater kd, the greater the damping ratio, the farther we get from the imaginary axis in that regard for imaginary poles, the lower the overshoot, therefore. Right? The overshoot decreases with the derivative gain. Nothing surprising here. That's the whole point of having it. But here's the proof that it will actually do what we want it to do. We can further extend this analysis to do the settling time. The settling time is a function of the damping ratio itself, but it's also a function of the natural frequency. And because the damping ratio increases with kd and the settling time decreases with the damping ratio, we can say that the greater the damping ratio, the lower the settling time, which means that the settling time decreases with kd. Both the overshoot and the settling time decreases with kd. Right? So for a overdamped, let's say for a mostly for underdamped systems, the greater kd, the faster we reach steady state. Now for a overdamped system, it's a bit different because the system is already overdamped. If we add a derivative controller to it, we are just taking away control action from it. We're giving less energy, so it may take longer. But if the system is underdamped and it has oscillations, the derivative controller will help eliminate those oscillations and make the system reach a steady state faster. So if I say, for example, the greater the derivative gain, the faster a underdamped system reaches a steady state. That's true. But the same cannot be said for a overdamped system because the overdamped system already has no overshoot. So you're just making it a bit slower. But the good news is once you have, for systems that have integral gains, there is some overshoot and KD can help compensate for that. Okay. So here is the summary of what each of these gains do. And this needs to be very clear. So let's start with the proportional gain. If we increase the proportional gain, overshoot increases. Now we can see that from the equations we just did as a function of Kp. Settling time, it has minimal impact, although we may tend to increase the settling time a little bit. And we'll make the steady state error decrease. The derivative gain, if we increase the derivative gain, we are increasing overshoot because you're giving more energy to the system. We are increasing the settling time because we are creating more oscillations. And the steady state error is 0. The steady state error doesn't increase with Ki. The steady state error is 0 regardless of the value of Ki, so long as it doesn't make the system unstable, so long as it's a positive value. Now for the derivative gain, If we increase the derivative gain, we decrease overshoot, we decrease the settling time for underdamped systems, and it has no impact whatsoever on the steady state error, right? So when you look at this table, I don't want you to memorize this table. I want you to think about what we were doing and complete this table in your head. If I tell you a proportion, an integral gain, and the integral gain always makes the steady state error 0, it is not something you have to just learn like that. You need to understand why it makes the steady state error 0. You don't need to memorize anything. Right? If you talk about, for example, the derivative gain, we know that the derivative gain decreases overshoot, but you need to go beyond that and understand why exactly it is decreasing overshoot, right? Just looking at it, memorizing a table. Okay, so this is a good summary of all these three elements in our controller, what exactly they do, and this has very practical applications everywhere. And once you get to your 4th year project, and if you're doing any sort of control, either in biomedical systems or any other systems, you will at one point use a PID controller, and you have to tune that controller. You now need to find the right balance between KP, KI, and KD, and that's not very trivial. And we'll see that in the next lecture, how we can tune these gains. Any questions here? No? Okay. All right. So let me give you an example. In this example, I'm proposing here, I have a DC motor. We addressed the model of the DC motor in one of the early lectures when we were looking at a simulation diagrams. I think it's like lecture 6 or 7, way back in the beginning. This entire transfer function here, this entire block diagram is a DC motor. It has its own feedback loop. This has nothing to do with the controller. This is an inherent feedback loop to the plant. There's no controller there. This is what you have circled in red here is an open loop system. We give it a voltage, and the voltage goes through the system and creates a speed at the output, the speed omega of S. Everything in here is part of the inner work of a DC motor. Now, if you want to add a loop to control the speed and to make the speed go to the value we want, now we can close the loop around the plant. And this is what we did here. We have a PID controller. You see all the 3 elements, PI, KP, KI, and KD. And then we have the feedback loop, because we cannot operate a controller without a feedback loop. So we are measuring the current speed of the motor, comparing that with a desired speed, creating an error, sending to the PID controller. The PID controller outputs a voltage, and this voltage is the one given out to the DC motor. That voltage turns into a speed, and the speed is measured back. So let's simulate the system in Simulink. I have here, just there. I'm simulating this in Simulink using these parameters for the DC motor. These are parameters of a commercially available motor. And I'm going to try 3 different controllers. The first one is a proportional control, only with KP, KI, and KD are set to 0. So it's a P controller. The second one is a proportional integral controller, PI, KP is 3, KP is 3, KI is 15, and KD set to 0. And then finally, a PID controller, where using the values that you see there. I'm going to give the system a step input, which means that I want the output to go to 1 radians per second and hold that, keep spinning at 1 radians per second. And let's see what the controller does. So here's the result for the proportional controller. Proportional controller is taking now, so you're giving here a step of 1 radians per second. The motor starts to spin. It kind of goes beyond its value because of inertia, and it will keep spinning, but at a slightly lower value than the actual value we want. We see the error in the second graph here. The error in steady state is never 0, because if it was, then no voltage would be applied to it. It would just stop. We take the error, we multiply that by KD. That's it. All right? And that is what we give to the motor. So some steady state error, some overshoot. Now let's add the integral controller. See what happens here, a lot more overshoot, but no steady state error. Now we see the error on the second graph. We're taking this error now, multiplying the error by KP. That's the yellow curve. Sorry, that's the red curve, the blue curve. Excuse me, that's the blue curve. We take the error as well. We integrate the error, multiply that by Ki, and that's the yellow curve. We then add them together. That creates a voltage, and that's the voltage given to the motor. What we see here is that in a steady state, only the proportional or the integral gain is doing something. You see here, it's not 0. Everything else is 0. And the voltage is held at a constant value that is non-zero because of the integral gain. But now you see how much overshoot we have. There's a bit of overshoot all over the place. And the settling time has also increased significantly. I look at the settling time we had here. We had some steady state error, but it would reach a steady state a lot faster. Now it takes a few more seconds to reach the same steady state. So let's bring in the... Yep.
Can I ask a question here? Are the two lower graphs voltage, or is it just the last one voltage?
Just the last one. This one is the integral plus, is just the error. So this is displaying the control action from, let's put it this way. This is the part of the portion of the voltage provided by each of them. When you add them together, that's the voltage. So it would simply be 1 over S times Ki error. Right? That's the yellow. And then error times Kp is the blue. And they are not yet voltages because you still have to add them up. So at this point, we are looking at the signals here and here.
Thank you.
Right? And then the voltage is after the sum there, which is this graph. Okay, now let's bring in the last part of our controller, the derivative controller, and look what happened. A small controller here. The steady state error is 0 because of the integral gain. The overshoot has decreased by a significant amount because of the derivative gain, and so did the settling time. The system reaches a steady state much faster. And you can do the same procedure again. We see in here the error in the second graph, and in the third graph we have the Pi and D contributions. In a steady state, only the integral gain is again doing something. And you look at the integral part now. The derivative part. You see that when the error changes a lot, that's when it has most of its effect. And in steady state, it does nothing. And what we see here is the final result, final voltage applied to the motor. We see a spike in the beginning here because the error is very large. We want the motor to start running. And as soon as we see that it's starting to reach the speed we want, we decrease, see it's now a negative voltage, we decrease the voltage a bit to now eliminate the, limit the overshoot that we see appearing there. And eventually the voltage becomes a non-zero value because of the integral control. A much better result compared to what we had here. Now, of course, these values here, they're not random. It takes a lot of tuning, a lot of trial and error to find a good compromise. And that's why it's important to have an accurate model. In some plants, you cannot afford to physically go there and change the PID gains and see what happens. Right? It could lead to some damage in the plant if you have this much oscillations, for example. So that's why with a model, we can analyze the behavior for different conditions. And then once we are sure, then apply that to the plant. Okay, so here I have two videos that you might find interesting. You can watch these ones later from a different lecture, a different course that also covered PID controllers. Not the entire lecture. You can just watch, I think, 5-6 minutes of each. And this one in particular has a demo that shows the effects of a PID controller using a linear cart that you're trying to control using it. All right, so watch this one, these two videos later. This summary is just a summary of all the effect of Ki, Kp, and Kg. And then the demo is the actual implementation using an Arduino as the controller. I have a controller C of S that was developed for the unstable plant shown. Why is this plant unstable? Because the plant has a positive real pole, which means that it's exponential, grows to infinity, which brings the whole system to instability. And the respective root locus of the feedback control system, so the root locus is the root locus of the entire system, as a function of k is presented. So we have two components in our controller. We have a function of S, C of S, and we have the controller that we are going to tune, controller gain k. So the characteristic equation for this system is 1 plus k times C of S times 1 over S plus 2, S minus 3 equals to 0. This is the characteristic equation, the denominator of the closed loop transfer function. And the root locus here is the root locus of that entire thing, as this value of k tends to infinity starting from 0. Based on this, indicate whether the following statements about the closed loop system are true or false. And let's look at these statements. Here they are. Let me display. Yeah, and now you have to look at your copy there. And I'm going to have it displayed here. The first statement is, the first three, we can just summarize this. Is the controller C of S a proportional, a PI, a PID, or a PD controller?
It's just a proportional.
It's just a proportional. Well, if it was just a proportional, let's think about it. If it was just a proportional, let me write it here. So we have the transfer function, the characteristic equation is k times C of S times 1 over S plus 2, S minus 3 equals to 0. Right? So if it was indeed a proportional, this would just be 1, right? It would just be 1. And we would have in the root locus only 2 poles. But in fact, we have a pole here, which is the -3 pole, the unstable -3 pole. We have a pole here that came from somewhere. We have a pole 0 right there, and yet the transfer function of the plant here doesn't have a 0. And we have another 0 right there. And here we have even another pole. This pole, particularly this pole here, is the pole at -2. Right? So something has changed, because if you only had the proportional controller, then we would have ended up here with only this pole and that pole. Yet now we have a 0 here, a 0 there, and another pole. Where did those come from? Well, they must have come from C of S. We must have somehow changed the transfer function to using C of S to now add these additional poles and zeros. So it's not a proportional controller, right? Because these extra poles and zeros must have come from C of S. So now the question is this a PI, a PID, or a PD controller?
Is it a PI?
It's a PI.
Sorry, PD. PD. No, I don't know.
Well,
Sorry.
it should be a PI or PID
controller.
Because there's one pole in the zero, so there should be something add, and then there should be an integral, but I'm not sure if there is a derivative of that.
Very good point. So one thing that we can say for sure is that there is an integral component somewhere, because this pole here appeared in the origin. That is coming from the integral part of something. But we also have two extra zeros. So what we added to this is two zeros placed somewhere and the pole. This pole here, this zero and that zero, A and B are just constants, right? Because this is what appeared here after the closed loop system, and these two poles here are coming from the plant. So what is this equation here? This is s squared plus s times a plus b plus ab, all divided by s, which is s plus a plus b plus ab over s. This appears to be C of s. All, of course, now multiplied by k, and k changes. What type of controller would this be?
PID.
PID, very good. Here is the derivative. KD is 1. Here is the proportional. KP is a plus b. And here is the integral, Ki equals to ab. We added two zeros and one pole. Here they are. So this must be a PID controller.
Could you please show again where the zeros come from?
The zeros are coming from here, what we added, the C of S, right? A and B. We noticed that there are two zeros, so I'm just creating an expression that has two zeros. We notice that there is a pole. I added the pole to my expression here.
Okay, and why isn't the denominator s represents the integral, right? So why isn't it s minus 3? Is it because there's still that pole on the positive real axis? It didn't like eliminate it.
Well, this is C of S only, right? This pole and that pole, they are still present. They are still there, right? This expression here only accounts for the extra pole at the origin and these two new zeros.
Okay. Okay.
So this is a PID controller indeed. The next question is, C of S cannot stabilize the system. Is this true or false? C of S cannot stabilize the system.
False.
Yes, it is false. Well, we can see here, right, that the pole that was unstable can enter the stable region, coming here and going there. As we use C of S as shown, A and B are just the values where they are placed, and K now is increasing from infinity. So as from 0 to infinity. So as it increases, this pole comes here, it's traveled downwards. This pole goes there, travels this way, and that to the 0, and this pole travels to the 0. Like that. So that's false. The next statement is the system is unstable for k smaller than 3. True or false? The system is unstable for k smaller than 3.
True.
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 True, right? So here k is 0, here k is 0.6, here k is 3. So anything is smaller than 3 will leave this pole in the unstable zone, and even that one, actually, the system will become unstable with two unstable poles. That's true.
Sorry, can I just ask one question before we move forward? For the last statement, you explained, you also explained it on the graph. Can you just quickly repeat what you said?
For the statement that says the C of S cannot stabilize the system?
Yes.
Yeah. So the graph shows that for low values of k, we have these two poles here that will be unstable, And as we increase k, they are coming together here. One goes up and then one goes down. And for a certain value of k, which happens to be 3, they enter the stable zone. The system now becomes stable because there will be no poles on the unstable zone. Right? So C of S can indeed stabilize the system just based on this graph. Right? We could come up with another version of C of S to eliminate this pole here, which would also be a valid way to make the system stable. Right? But what we want is that for a given operating point, for a given value of k, we have a condition where the system is stable. And here we have plenty. So long as k is greater than 3, the system is stable.
Oh, okay. So this graph is actually C for multiple values, or am I wrong?
This graph here, for every point along this graph, we have one value of k. This k here. Not these ones, right? That k that is changing from 0 to infinity. Right, so this is basically a collection of the location of all possible poles of the closed loop transfer function as k goes from 0 towards infinity.
Thanks.
Okay. All right, so the next statement is the system is stable for k less than 3. Well, that's false. Next one is when k equals to 18, the system is critically damped.
True.
True. Right, when k equals to 18, we are right here. The two poles are the same. And this characterizes a critically damped system indeed. The next one is when k equals to 0.6, the system is critically damped. True or false?
False, because it's unstable.
Right, that's false. Even though the poles are the same, they are in the unstable region, which makes the system unstable, and that takes over the critically damped or whatever, right? So when k equals to 0.6, the system is unstable. When k equals to 0.6, okay, that's we did. K equals to 3, the system oscillates at 2.5 radians per second.
True.
True. When k equals to 3, poles are here and here, and they happen to cross the imaginary axis at 2.5 radians per second. You see here negative 2.5 j. And this is simply the natural frequency at which, or the frequency at which it will oscillate indefinitely. So that's true. Next one is when k tends to infinity, the system is stable. True or false? When k tends to infinity, the system is stable. Yeah, that's true. When k tends to infinity, this pole here will go to negative infinity. It's stable. This pole here is going that way, and to this 0, still stable. This pole goes to that 0, stable. System is stable. Next one is for k greater than 3 and smaller than 18. K greater than 3 and smaller than 18, the system is underdamped.
True.
True. All right, so k is greater than 3. We are here. And k is smaller than 18 there, so we are either here or here. And because along these lines we have complex poles, we have an imaginary part that characterizes a underdamped system, and the system is indeed underdamped. Okay.
What was the answer for the one where it was oscillating at 2.5?
It was true.
Okay, it was true.
Yeah.
Why?
Because at 2.5, when k equals to 3, we are here and there. We are along the imaginary axis, and we are crossing the imaginary axis at 2.5 radians per second. The point where we cross the imaginary axis is the frequency of oscillation.
Okay.
It's the natural frequency, right? Natural frequency being always the distance that separates the pole, the Euclidean distance between the pole and the origin. For k greater than 18, the time response is an exponential response.
True, because in that way there is only the real part, and so it's exponential.
Right. For k greater than 19, we are only on the real axis. We passed the critically damped point. The system is now overdamped. Next question is, a PI controller can stabilize the system. A PI controller can stabilize the system. So this one is a bit tricky.
So that means, sorry, so that means we just ignored part of the derivative and think about it. Okay. Do you think it's true? Because if we ignore the 2 0 pause, and then it can still approach some stable.
Well, let's see, because this graph here is only valid for a PID controller.
Oh, okay, I see.
If we want to use a PI controller, then we would have something like this: S plus A divided by S, which is 1 plus A over S. This is the proportional. This is the integral. And the original is now the root locus is something we need to recalculate, probably now using MATLAB. So I wouldn't give you this question in an exam because we didn't cover how to do the root locus, but let me draw this for you here. We would have the pole at 3. I have the pole at -2. Now we added a pole there. And we could place, if we set A to 3, we could place the 0 on top here. So these two cancel out. These two will come together. One goes upwards, one goes down. And now the system is again stable because this pole, this unstable pole disappears, and all other poles as k goes from 0 to infinity, this k there, right? Remember that this is C of S. I will make the system stable. So why would we bother if a PI controller can stabilize the system? Why would we bother with a PID? What is the advantage of the PID here compared to this one? So the statement is true. A PI controller can indeed stabilize the system. So why bother with the derivative part?
Get off the oscillating.
This will also oscillate so long as you are there. There's some oscillations, right? Both will oscillate.
The PI would oscillate till infinity, but with the PID controller, when k is 18, as k tends to infinity, it's overdamped.
Right. So good point. So when this k is very large, it's just overdamped. When this k is very large, we are tending to infinity here, is underdamped. It's a good point. But we could, for instance, just limit k here to this point, right? To the critically damped point. We didn't have don't have to pass that point. But the main advantage is that here we need this value of a to be precisely 3. If we don't know the plant exactly, we can never achieve this in practice because we need to cancel out that pole precisely. Whereas here, we can play around with this pole and 0. This pole and 0 they don't need to be exactly there. We could move them around, right? And the system would still maintain stability provided that we have a sufficiently large k. Whereas here, it's only stable if we are able to identify exactly where this unstable pole is and then place the controller exactly at the 0 from the controller exactly in the same location. It's doable, but it's a lot more complicated than something like this because here we have a lot more freedom. You don't need to be precise. You can play around with these poles and zeros. It will still be stable. Here, there is no room for that, right? So if for some reason we can't identify this pole, we have to go with this. Or if the system changes slightly during operation, these parameters change a little bit, and the system will not hold this configuration and all of a sudden become unstable, right? So the PID controller for this particular example is a much better choice. Okay, next one is proportional controller can stabilize the system. That's false. We discussed that one in the beginning. For k equals to 3, the damping ratio is 0. True or false? For k equals to 3, the damping ratio is 0. True or false?
I want to say false.
For k equals to 3, we are on the imaginary axis right here. Right, we have an undamped system. And this happened indeed when the zeta is 0. Right, that's true. Okay. And for k tending to 0, the system is overdamped. True or false? For k tending to 0, the system is overdamped. True or false? That is?
It's unstable.
That is unstable. Right? When k tends to 0, this pole is here, but this pole is around its unstable zone, and the system is simply unstable. So that's false. Okay. So this question came from final exam. And you notice here there are 3 options, T, F, and D. So true, false, and D stands for don't know. But the way this question was applied is that for every correct answer, we had a positive like 0.5 marks. For every wrong answer was negative 0.3, something like that. And for D, don't know, would just be 0. So people couldn't guess. Of course, I'm not going to do that. Right? But I did it once. Didn't go very well.
Professor, have we done the k bigger than 80?
For k bigger than larger than 18, everything is overdamped. Right? Yeah. K larger than 18, this one is real. This pole here is also real. This one will be somewhere around here, is overdamped. Okay, so the one says for k greater than 18, the system is overdamped. Yes, that's true.
Sorry, can I just ask a quick question? Yep. We on the first poll from the right, we had written a tree there. Was that S?
This point here?
Yes, we had written like a tree.
Yeah, that's this tree here.
Oh, okay. Thanks.
Okay, so let's do another exercise quickly. Let's do this one over there. Yeah, so that's exercise number 5. We'll probably go a little beyond time today, but I want to do this one and then I'll let you go. So we'll probably go over time. If you're free to leave now, I'll post this later anyways. But if you want to stick around for this example, it should take 5 minutes. So here we have this exercise. Consider the following closed loop system. It's simply the controller and the plant transfer function. Here we have the 2 functions. The question is find K and P so that the system has a 10% overshoot to a step input and a settling time of 1.5 seconds. So clearly the controller here is can be considered as the integral controller. And we want the system to have a 10% overshoot to a step input and a settling time of 5 seconds. So I rearranged the problem here a little bit. So just to highlight, I kind of swapped the order here just to show that this is an integral. That's the plant. We want a percent overshoot of 10%. And we want a settling time of 1.5 seconds. So this is a typical question I may get on a test. So what would be the first step here?
Transfer function?
Transfer function. What is the transfer function at this point? We should be able to just look at this and write the transfer function. And what is it? Okay, you can follow the steps later. Times S plus P plus K. And I'll do the full solution later, but this is equivalent to K over S squared plus PS plus K. Okay, so that's step one. What do we do next? We have the transfer function. The transfer function has a characteristic equation here that depends on K and P that we need to define. And we want to meet these two criteria here. What do we do next?
We want to find a dampening ratio for the 10% overshoot, so then we can find P.
Very good. So we can find the percent overshoot from the percent overshoot. We can find a damping ratio. By simply equating these. Remember that this 100 here is already to put this in percentage. Right? That's where this 100 comes from. So here, nothing. We don't need anything else from this equation. From the percent overshoot, we can find the damping ratio. There's only damping ratio there. So for it, which is 0.59. 0.59. Okay. What do we do next? We have the damping ratio. We need to work our way towards P and K. What do we do next?
Oh, in your answer for exercise 5, it says zeta is 0.7.
This is correct.
Okay.
Yeah. So what do we do next?
Would you find that omega n from K is K, a square root of K, and then use that with P? It's like to the damping ratio omega n equals P, right?
Right.
And then you can
Right.
make it a system for K and P, or one equation for K and P.
Yes, we can make an equation for damping ratio and P, another one for omega n and K, but we still don't have omega n. All right, so we could take omega n from the settling time first, just to simplify things a bit. We know that the settling time is 4 divided by zeta omega n, which means that omega n is 4 over zeta times Ts. And this is 4 over zeta 0.59 times Ts 1.5. And this is 4.519 radians per second. Now, yes, now we know the characteristic equation as S squared plus 2 zeta omega n S plus K. Sorry, plus omega n squared. Yeah, do you have a question there?
Yeah, is that 4?
That's a 4, yeah, 45019. Now we can say that omega n squared equals to K. Right? We're just equating these. Well, we have omega n, K equals to 4.519 squared, which is 20.42. I don't know where I found that 19. That 19.75 on the slide is not correct. And now we can equate to the last part of the equation here as well. We know that a P equals to 2 zeta omega n. From that, B equals to 2 times zeta, 0.59, times 20.42, which is approximately 24.39. Okay. Easy question. The
Subbed in K instead of omega n. Like you should sub in 4.519 instead of 20.42, right?
did I? Oh yeah, right.
So it shouldn't be 24.
So omega n, yeah, I need to replace K. Thank you. So that's omega n is 4.519. And what is the multiplication here now?
I think it's 5.34.
134. Okay, good. So yeah, so that's better. Yeah, I indeed multiply this by K accidentally. Easy question. The key is to find it correctly, the transfer function, and this is a must know. Given a feedback loop like this, you must be able to find a transfer function. With some practice, you'll see that it's really simple. You don't need to go through the steps every time.